Our center really focuses on addressing a problem that's related to plastic waste. So right now, most of our plastic is generated from petroleum sources. There's a tremendous amount of non-renewable carbon that goes into the production of plastics, both in the plastics themselves, but in their generation. We do our very best to throw them away, to recycle them, but even in the ideal waste collection processes, we're losing somewhere between 30 and 40% of that waste, and that's going into our environments. Currently, right now, we are on track to have as much waste in the ocean as fish, but the real problem that exists is our ability to fully explore the material design space.
Synthetic biology materials are materials that produce from biology, but they are also different from materials naturally produced by nature. They are the materials that does not exist in nature, but we engineer them and we produce them using biology. And in our particular case, we engineer bacteria to manufacture these materials.
Well, the most fascinating aspect of this project is how we bring together so many different disciplines to understand how nature can take molecules and produce the same fibers that we use to generate clothing and other types of fiber-based products. In order to understand this, you really need to understand the chemistry, the biology, the manufacturing aspects, the life cycle environmental impacts, and it takes really a melding of different minds, and that's really fascinating.
This is important for many reasons, including environmental factors. So we don't want plastics to end up in the oceans, and we want to come up with more sustainable alternatives for these materials and ones that can be manufactured environmentally. And in the context of this, of course, there are many challenges. We need to understand the physical behavior of protein-based materials, understand molecular interactions that govern the overall macroscopic mechanical behavior of these materials. And as part of that, we utilize computational models, which include molecular simulations and machine learning, to figure out some of the mysteries around what kind of sequences might result in mechanical properties that are superior to fibrous materials we use today.
I've really benefited from the team dynamic that comes with working on such an interdisciplinary center. We have a great diversity of backgrounds and technical expertise, and being in the center has helped me learn not only scientific skills, but also social skills that will allow me to learn what other people are capable of. And I think that's the most important thing in developing interdisciplinary innovation, is kind of recognizing people as the tools rather than the scientific knowledge that we have. People are really the thing that we need to achieve these goals.
These large societal challenges, these challenges are very difficult to solve, not only because of the technical issues, but because any solution is going to require human, and thus changing human behavior, or at least understanding human psychology and behavior. And so to address these, this is require a transdisciplinary team that integrates disciplines from all over the university, ones that understand things about materials, that understand things about biology and synthetic biology, the systems that we're using to produce these materials, that understand about the various products that we may be developing, the applications that we are in, and then understand humans. So by putting ourselves in the room with people who have different lived experiences and expertise, it allows us to break out of that box. And so that's our goal in this project.